Okay, on this video, we're going to talk about what limits are and what we're going to look at it from a graphical standpoint, first of all, and then we'll do some limits where we use some algebra. Okay, so here's what a limit's all about. It's a good tool to use a piecewise function to talk about limits as a good starting point. So here we have the piecewise function made up of x squared plus 1. When x is less than or equal to 0, that would be a parabola shifted up 1. Notice I'm only graphing it when x is less than or equal to 0, so we're actually going to stop. It's only going to be the left half of the parabola. From 0 to 3, we're graphing the line y equals x plus 1, which has a y-intercept of 1 and a slope of 1. Notice the equal sign is not on the 0, so it's actually an open circle, but the parabola was going through the same point and had a closed circle, so it's going to look like it's closed there. But at the end point at 3, if you plug in 3 into that line, you're going to get a y value of 4, but there would be a hole there in the graph. When x is greater than or equal to 3, we're graphing the square root of x plus 1. The full graph would start at x equals -1, and it's a square root graph, so it would bend to the right. But since we're picking it up at 3, if you plug 3 into the function, the square root of 4 is 2. So we're going to just see it from here on out, okay? So that's our graph. So here's the idea of a limit. What does our y value approach as x approaches 0 from the left side? That's kind of like saying in this function, what is f of -0.000001? Something really close to 0 but slightly to the left. Well, if we're to the left of 0, we can tell we would be on the parabola, but this number is so close to 0, we might as well just plug 0 into our parabola, in which case we're going to get 1. Okay? If that makes sense, this is exactly or pretty much the same thing as what we mean by a limit. So how we would write this in calculus, we would say the limit, LIM, as x approaches 0, because our number was a little bit less than 0, you can think of that as the number is getting close to 0 from the negative side, or we often read that from the left side. And so what this is saying is if we get infinitely close to 0, the y value we're going to see is 1. What does y approach from the right on the graph as x approaches 0 from the right? That would be denoted as the limit as x approaches 0 from the positive side. Usually when we come from the positive side, we're coming from the right side of my function. Let me go back to my graph for a second. If we were approaching 0 from the positive side, we would be on the line graph. And if we were getting infinitely close, if x was getting infinitely close to 0, our y value is going to be getting infinitely close to 1. So what we did here is if you plugged in, my graph here was x plus 1. So if you just put 0 in for x, we're going to get a y value of 1. Okay. Now, both the limit as x approaches 0 from the left side and the right side are both giving me 1 as an answer. And so if we look at, for lack of a better term, the neutral limit, meaning x is approaching 0, but we're not indicating which side. Well, both sides, you can only approach 0 from the left or the right side, and we're getting 1 for both answers. So if those one-sided limits both give you the same answer, then the overall limit is going to be 1 in this case. So if the limit as you approach a number c from the left side is exactly the same as the number you get when x approaches c from the right side, and let's say that number is L, then the overall limit as x approaches c of that function is going to be L. Now, let's compare that. Let's do the same two one-sided limits near x equals 3. Let me go back to our graph for a second. As you can tell, when x is near 3, it depends on which side of 3 you're on as to which function you're on, right? If we're a little bit to the left of 3, we're going to be on the line. If we're a little bit to the right of 3, we're going to be on our square root function. And so to figure out those one-sided limits, if we're approaching 3 from the positive side, we're going to be on the square root function. And you could just, we're so close to 3, you can't even tell the difference. So we might as well just plug in 3, and that's going to give us a limit of 2. Graphically, you can tell that's true. If we get close to 3 from the right side, the y value we're getting closer to is 2. If we approach 3 from the negative side, we're going to be on the line, and our y value is going to be getting closer to 4. That could be confirmed from the graph. If we approach 3 from the negative side. Now remember, even though there's an open circle there, when we talk about a limit, x is not equal to 3, x is approaching 3. So the idea is if you got infinitely close to 3, the y value you're expecting to get to is 4. And so that would be your limit as x approaches 3. Now in this situation, notice the two one-sided limits are giving us different answers, which means the overall limit as x approaches 3, it depends on which side we're approaching 3, so we just say that the limit does not exist. And so this is true in general as well. If the limit from the left side of a number does not equal the limit as x approaches that number from the right side of your function, we're getting different answers, then that limit does not exist. Now, it's also, I think, worth noting that if x was approaching a value, like let's say right here at -2, okay, when x is near -2 from either side, right, from the left or the right side, we're approaching the same y value if you get close to x equals -2 from either side. So if someone wanted to know what's the limit as x approaches -2, you don't need to look at the left and right hand limit. How do I find the limit? I would just plug the -2 in. So the limit as x approaches -2, I would just plug -2 into the parabola, right? Because that's the part of the function we'd be on. And that would give me a value of 5. Okay, so our next example, it's nice to be able to check out your limits from a graph. You should know how to do that. If someone gives you a graph, you should be able to read off some limits from the graph. But my next example, I also have a piecewise function. And if you look at the pieces, I mean, that's a cubic graph. They've got a cube root graph. This is not going to be so easy to graph. And so my recommendation here is don't graph this. It's too messy. But you still should be able to answer some limit questions even without the graph, now that we know something about limits. So let's start with this. If someone asked the limit as x approaches 1, the thing you would want to notice is the way our function's defined, you would be on a different piece of the function if you're less than 1 than if you were a little bit bigger than 1, you would be on the middle piece. And as we saw, if the left and right hand limits don't agree with each other, the limit won't exist. So what we better do first is look at the two one-sided limits. The limit as x approaches 1 from the left side. Remember, you're using numbers less than 1, so you'd be on the cubic function, and you could literally just plug 1 in. That gives me a limit of 3. If we approach 1 from the right side, we're close to 1, but we're bigger. And if I plug in 1 there, I get an answer of 6. Now that we see the two one-sided limits don't agree with each other, the overall limit does not exist. Okay. Now let's try the limit as x approaches 8. Once again, if you go back to your function, you can tell we would be on a different piece depending on which side of 8 we're on. So before we answer the overall limit as x approaches 8, we should look at our two one-sided limits again. This time, however, if you do the limit as x approaches 8 from the left side and plug in 8 to the middle piece, we get 7. And from the right side, for x minus 1, we're going to also get 7. So now it's a safe thing to say that the limit as x approaches 8 is 7. Okay, and then finally, like my last example, if we wanted to know the limit as x approaches 10, what you would want to notice then is, going on back to my function, if I'm near 10, if x is near 10, and when I say near 10, I mean really close to 10, like 9.9 or 10.1, can you see that I would be entirely on this function if x was near 10? And there's not going to be any transition from one piece to the other. So in this case, we don't need to check the one-sided limits because both sides of x equals 10 were on the same function, which is y equals x minus 1. So to find that limit, I just take the 10 and plug it in. This is going to be your first rule of limits. If you get a number, you want to just try plugging it in. For example, we did a couple of piecewise functions to explore limits as our first example, but many times it's not a piecewise function, it's just a function. Okay, here I want to know the limit as x approaches 2 for x squared plus 4x plus 3. We know what that graph looks like. It's a parabola. Okay, and we also know that a parabola, doesn't have any breaks in it, like we saw on our first graph. Okay, so we know, okay, and this is a word that's we're going to be talking a lot about. It's a nice continuous function. And we know that if we approach 2 from the left side or the right side, if x got close to 2 from either side, I would be getting the same y value. So how do I find this limit? Just like I said before, we're just going to plug it in. Plug in the 2. And that gives me a limit of 15, which would be your y value. It's that easy. Well, sometimes. Okay. Things get a little more complicated. Let's check out this limit. If I plug in 9, I get 81 minus 90 plus 9 gives me a value of 0. And if I plug in 9 to the bottom, I get 0. Okay, so this is very interesting. Your whole math career, you've been taught if you get 0 in the denominator, that doesn't exist. And that is still true. Okay, but what we have to remember here is when we get this answer of 0 over 0, these aren't really 0 because, again, x is not really 9. It's approaching 9. So in reality, what we have is a number that's really close to 0 divided by a number that's also really close to 0. Okay? So we're not really dividing by 0. We're dividing two small numbers. Okay? So, but we call these kinds of limits, when you get 0 over 0, we call them indeterminate. And what that word means is that just knowing the limit is 0 over 0 doesn't help you determine what the value is. Okay? So how do we sort this out? Well, let your algebra skills kick in here. If we factor the numerator, we get a common factor of x minus 9, which cancels out, and that just leaves me with x minus 1. And so now if I take the limit as x approaches 9 for x minus 1 and just plug in, I get 8. I also think we should understand what's going on graphically here. So graphically, what's happening is the graph of this function looks kind of complicated, but as we saw, if you do the algebra, it really just looks like the graph of y equals x minus 1, which would just be a line with a y-intercept of 1 and a slope of 1. It would look like this. However, okay, this goes back to domain. This is why we wanted to talk about domain before. The domain of this function right here is x cannot be 9, right? If you do plug in 9, you will get 0 in the denominator. So we have to remember that x cannot be 9. So even though the x minus 9s cancel out, and this looks like just the line y equals x minus 1, we have to reflect the fact that when x is 9, it's not defined. And so what happens is there's a hole in the graph, okay? This graph looks just like the graph of y equals x minus 1, with one exception. There's a hole at corresponding when x is 9, and guess what the y value is right here? Well, we figured it out. As we approach 9, that limit is going to be 8. Okay. So let's try some more. We've got x approaching 2, 4x squared minus 3x minus 10 over 6x squared minus 12x. If you plug in 2 to the top, you're going to get 0. And if you plug in 2 to the bottom, you're also going to get 0. Okay? So another indeterminate form, right? Remember, it's not really 0. It's approximately 0 over approximately 0. So this time I'll do some factoring. It's a little more involved. Okay, check your factoring skills. Here you can just take out a 6x from the denominator, but you do get a common factor of x minus 2. Okay, which if you think about it, had to happen because we know if you plug in 2 to the top, you get 0. So we also should be getting a 0 in the factored form, which is why, does it make sense why there has to be an x minus 2 factor? Because if you plugged in 2 there, that would make that 0, and that would make this 0. Okay, that's a nice helpful hint when you're doing limits. Once those cancel out, if I plug in 2, I get an answer of 13/12. Okay. Let's try another one. And maybe what would be a good idea is pause the video, write down the limit, and maybe give it a go. It's a 0 over 0 limit. See if you can do some algebra. All right, so now we'll run through it. And that hint that we learned from the last problem is very useful. Because when we plugged in 3 to the top and the bottom, we got 0, we know there has to be a factor of x minus 3 in the top and the bottom. Okay, and then you can kind of work backwards. You could just say, hey, what is this going to have to multiply out to get me 2x squared? Well, there has to be a 2x. And in order to get a minus 3, this had to be a positive 1. You maybe recognize the denominator as a difference of cubes. And if you've forgotten how to factor that, which is not uncommon, a lot of people learn it and then quickly forget it, we could take advantage of the fact that there was an x, we know there's an x minus 3 factor, and you could kind of think backwards. What would you have to multiply by to get x cubed? There would have to be an x squared. What would you have to multiply to get negative 27? There must be a positive 9. And if you think about the middle terms, there's a negative 3x squared and a positive 3x squared. So that's how you would know this has to be positive 3x, because we don't have any x squared terms in the final answer. Okay, bottom line is, once those cancel out, you plug in 3, you get an answer. Okay. Sorry about that. All right, so here's another situation where if you, how about I do this? There we go. If you plug in 5 to this square root, you get square root of 9, 3 minus 3, which is 0, 5 minus 5 is 0. In this situation, though, factoring is not going to be helpful here. So what are we going to do? We're going to do another algebra trick you might remember, which is the conjugate. Okay. Conjugate, if you recall, if you have a root minus a number or even plus, you just multiply by the opposite, just change the sign. And I'm going to do top and bottom so that I'm only multiplying by 1. I can't change the problem. Okay, and if you FOIL this out, square roots cancel each other. The middle terms will cancel out because they have opposite sign, and then I end up with a minus 9. Notice that x plus 4 minus 9 gives me an x minus 5, which is what I have in the denominator, which is why I'm not going to distribute in the denominator. I have to anticipate that those two terms are going to cancel, which they will. Once they do, I can now substitute in 5 and I get an answer of 1/6. Okay. We can do limits with trig functions. If x approaches pi over 2, the sine of pi over 2 is 1, so I have 1 minus 1 is 0. Cosine of pi over 2 is 0, so it's another 0 over 0 limit. So how we're going to sort this one out is we're going to multiply top and bottom by what I call the trig conjugate. So in the same spirit as how we did the regular conjugate, we're going to multiply top and bottom of this expression by 1 plus sine of x. We're just changing the sign. And what we're going for here, when you FOIL this out, you have 1 minus sine squared on the top, and this is where it's good to know your trig identities. 1 minus sine squared of x is the same as cosine squared x. And now we can see that one of those cosines will cancel because I have 2 powers of cosine in the top, leaving me with cosine over 1 plus sine. And if I substitute in now pi over 2, I get 0 over 2, which is 0. One more. Now I plug in 2, I get 10 over 2, 5 minus 5 is 0, and denominator is 0. So what can I do here? Well, I don't see any factoring, I don't see any conjugate, but I do see that if I have a fraction, I could rewrite the top with a common denominator, x over x. That's going to give me 10 minus 5x over x. And then what I'm going to do is take the x minus 2, think of this as over 1, and then multiply by the reciprocal. So that's over here now. If you factor out the negative 5 from the top, we get our x minus 2's to cancel out. Plug in 2, and you get negative 5 over 2. Okay, so one thing from these last examples that we learn is that if you get 0 over 0 on a limit, what have we seen that can solve it? We can factor, we can do a conjugate, we can find a common denominator. All of those are skills that we learn in algebra. And so the phrase I use a lot is if you get 0 over 0, do some algebra. Okay, I'll be saying that, I know, on future videos as well. So in the next video, we're going to look at some indeterminate limits where even the algebra may not be as useful, but there are still ways to solve indeterminate limits if algebra doesn't work.